Hi, I am Dr. Goodmanson with a rapid derivation video intended for the readers of my book, General Aviation Aircraft Design, Applied Methods and Procedures. In this video, I will show how the ideal gas law is derived. First, however, we should review the timeline of the discoveries of the various gas laws. It helps one understand and put in perspective how and when the ideal gas law was discovered. In 1662, the Anglo-Irish natural philosopher, chemist, physicist, and inventor Robert Boyle discovered that the product of the pressure and volume of a gas in a container is a constant. This is known as Boyle's law. 17 years later, in 1679, the French physicist Edmond Mariotte, excuse my pronunciation, discovered the same relationship. Unfortunately for him, the honor of the law had already been bestowed upon Boyle. In 1780, the French inventor, scientist, mathematician, and balloonist Jacques Charles discovered that the ratio between the volume and temperature of a gas is a constant. This is Charles's law. In 1802, the English chemist, physicist, and meteorologist John Dalton demonstrated that the total pressure in a mixture of gases is the sum of the partial pressure of each constituent gas. That same year, the French chemist and physicist Joseph-Louis Gay-Lussac discovered that the ratio of the pressure and temperature of a gas is a constant. This is Gay-Lussac's law. 9 years later, the Italian naturalist Amedeo Avogadro discovered that the ratio of the product of the pressure and volume of a gas divided by the product of its number of moles and temperature was a constant for all gases, and the value of this constant was the same for all gases. This discovery is called Avogadro's law. In 1834, the French engineer and physicist Émile Clapeyron used this law to show that the laws of Boyle, Charles, and Gay-Lussac could be combined into a single law, the ideal gas law. All right, let's derive this law. Avogadro's law in molar form is given by this expression, where the parameters P, V, T, and N are defined as shown. Note that the volume V is stricken through to distinguish it from the V we use for velocity or speed. The constant is frequently denoted by R with a bar above it, R bar, and it is called the universal gas constant because it has the same value regardless of the gas. Now, rewrite the expression as shown and replace the number of moles N by the ratio of mass to molar mass. This is written as shown. Continue by dividing through the expression by the mass, m. Note on the left-hand side that the ratio of volume to mass is the inverse of density, while mass is eliminated on the right-hand side. The resulting expression is shown. Note that we will now redefine the ratio of the universal gas constant by the molar mass of the gas and call it the specific gas constant. We denote this by capital R. Unlike R bar, it is unique or specific to each gas. Therefore, we write this simply as R times T. We now write this as shown. Pressure is equal to density times the specific gas constant times the absolute temperature. This is the ideal gas law. It is also known as the equation of state.